In this lesson, we focus on what happens when code breaks, and, more importantly, how to handle that break in a controlled way. In Python, errors often show up as exceptions, a signal that something unexpected happened while your program was running. If you don't handle them, the program stops. If you do handle them well, your code becomes more robust, safer to run, and much easier to maintain.
The mindset shift here is that errors aren't just bad news, they're information. They tell you what failed, where it failed, and often why. And once you start writing programs that interact with real inputs, files, user data, external libraries, exceptions become normal, not rare. So the goal is to learn how to anticipate common failure points and respond in a clean way instead of letting your script crash.
In this lesson, we'll make error handling feel concrete. First, we'll clarify what we mean by errors versus exceptions in Python, because that vocabulary helps you reason about what's happening when code fails. Then we'll look at the most common exceptions you're likely to meet in everyday code, so you can recognize them quickly and understand what they usually mean. Finally, we'll practice the core mechanism for handling failures: try and accept.
The practical goal is safer, more robust code, especially for analysis work. Real data is messy. Files can be missing, values can have the wrong type, inputs can be malformed, and assumptions break all the time. Instead of letting a script crash at the first surprise, you'll learn how to catch the problem, respond with a clear message, and either recover or stop gracefully. That's what makes your code dependable in the real world.
In Python, it helps to separate two ideas. An error can be something the interpreter detects before your program even starts running. Classic example, a syntax error. An exception, instead, happens while the code is executing. The program starts, but then it hits a situation it can't handle. This distinction matters because syntax problems must be fixed in the code, while runtime exceptions are often about data, inputs, or conditions that can change from one run to another.
Look at the example. The logic is clear, but the structure isn't valid Python syntax. Because of that, Python can't even begin execution. It stops immediately and points you to the line where it got confused. That's different from a runtime issue, where the code is syntactically fine, starts running, and only crashes when it reaches a problematic value or operation. So first you make the code runnable, then you learn how to handle the surprises that happen during execution.
Runtime errors are the ones that happen while the program is already running. The code is valid Python, so execution starts, but then an operation fails at a specific moment. In Python, that failure is reported as an exception, and by default it stops the program right there. This is why exceptions matter. They're not about bad syntax. They're about something going wrong with a particular operation, often depending on the values your code receives.
In the example, the code tries to convert a string into an integer. That works only if the string actually represents a number, like 42. But here the content isn't numeric, so Python raises a value error. Basically, I understand what you asked, but this value can't be converted. And unless you handle that exception, the script ends immediately. This is a perfect preview of why we'll use try and accept so the program can respond instead of crashing.
Runtime errors are the ones that happen while the program is already running. The code is valid Python, so execution starts, but then an operation fails at a specific moment. In Python, that failure is reported as an exception, and by default it stops the program right there. This is why exceptions matter. They're not about bad syntax. They're about something going wrong with a particular operation, often depending on the values your code receives.
In the example, the code tries to convert a string into an integer. That works only if the string actually represents a number, like 42. But here the content isn't numeric, so Python raises a value error. Basically, I understand what you asked, but this value can't be converted. And unless you handle that exception, the script ends immediately. This is a perfect preview of why we'll use try and accept so the program can respond instead of crashing.
The key idea is that exceptions don't have to crash your program. With a try/accept structure, you wrap a risky operation in a try block. If it succeeds, Python just keeps going normally. If it fails with a specific exception, control jumps to the matching except block, so you can decide what to do next instead of stopping execution.
Here the risky line is converting a non-numeric string to an integer. When that conversion raises a value error, the except block runs and prints a message so the script stays alive. In practice, this is how you make code resilient. You handle predictable failures right where they can happen, and you keep the rest of your program running safely.
Think of this structure as a full control panel for failure handling. The try block contains code that might fail. The except block catches specific, expected problems and lets you recover. The else block runs only when the try block succeeds, which is useful to keep this success path clean and separated from error handling. And finally is the safety net. It runs no matter what, success or failure, so you can guarantee cleanup actions.
In this example, the risky step is turning user input into an integer. If the user types something non-numeric, you land in the ValueError handler and show a friendly message instead of crashing. If the conversion works, the else block is where you do the normal follow-up work with the valid number. And finally runs in both cases, so it's the perfect place for always do this actions, like closing a file, releasing a lock, or disconnecting from a database.
When you write exception handling, the goal isn't to catch everything. It's to catch the problems you actually expect and let the rest surface so you can fix them. This pattern shows how to handle multiple exceptions explicitly by stacking multiple except blocks. Each except targets a different failure mode, which keeps behavior predictable and makes debugging much faster.
Here there are two realistic ways things can go wrong. The user can type something that can't be converted to an integer, and then you get a value error. Or the user can type 0, conversion succeeds, but the division fails and you get a zero division error. Separating the handlers means you can give the right message for the right problem. And if neither error happens, the else block runs and prints the computed result. So the success case stays clean and easy to read.
Exception handling is for expected runtime problems, situations where your code is correct, but the world around it is unpredictable. The key mindset is, if a failure can happen during normal use, and you can recover or provide a meaningful fallback, then it's a good candidate for try/except. This is very different from using exceptions to hide bugs or sloppy logic.
Think of the classic real-world categories. Users will type weird input, files can be missing or corrupted, and external data can be messy. APIs time out, CSVs have bad rows, JSON can be malformed. In those cases, handling the exception lets your program keep going in a controlled way, maybe by asking again, skipping a bad record, or logging what failed. But if the problem is a logic error like the wrong formula, the wrong variable, or a broken branch, catching it just masks the bug. And one more subtle point. Don't use try/except instead of validation. Validate what you can up front, then use exceptions for what you can't reliably predict.
In data analysis, error handling is not just a defensive programming habit. It's part of the scientific method. You're working with inputs you did not fully control. Data can be incomplete, inconsistent, or formatted in unexpected ways. So the goal is not merely to prevent crashes, but to make failures informative. Detect them early, classify them, and decide whether to stop, skip, impute, or flag. In practice, robust pipelines treat data issues as first-class events. They produce logs, summaries, and quality metrics that let you quantify how much cleaning happened and how much uncertainty you introduced.
A good mental model is, every step in the pipeline has predictable failure modes, and you plan for them. Files might not exist because the path is wrong or the dataset wasn't delivered. Rows can be malformed in CSV/JSON. One broken delimiter can shift columns and silently poison your analysis if you don't detect it. Derived metrics can blow up with division by 0, so you either guard the denominator or define a safe fallback like NaN. Type conversions are another classic. Numbers stored as strings, commas versus dots, or hidden characters that break parsing. And then there's corrupted data. Missing values, invalid dates, out-of-range values, which often aren't programming bugs at all, but a genuine property of real-world datasets. The win is when your code doesn't just fail or succeed. It tells you what went wrong, how often, and what it did about it.
Effective error handling is really about engineering trust into your code. When your analysis runs end-to-end without surprises, you can reproduce results, debug faster, and collaborate without fear that a tiny data glitch will derail everything. The key is to design failures so they are controlled and meaningful. Use clear exceptions when something is truly impossible, recover gracefully when it's expected variability, and always leave a trace, logs, counters, or summaries, so you can audit what happened. In other words, don't aim for code that never fails. Aim for code that fails well.
And the biggest enemy is the silent failure. Crash is annoying, but it's honest, at least you know something broke. Silent failures are worse because they can produce clean-looking outputs that are wrong. That's why surface errors clearly matters. Validate assumptions, assert critical constraints, and when you catch exceptions, don't just swallow them. Record context and decide what the correct fallback behavior is. Sometimes the right move is to stop the pipeline with a loud message. Other times it's to skip a bad row and keep going, but only if you track how many you skipped. The practical goal is resilient code. It survives bad data, but it also tells you exactly how messy the data was and what it did to survive.
Before we wrap up, here's the big picture. Error handling is what makes your code reliable, but it doesn't automatically make your code scalable. When your projects grow, you need structure, ways to organize state, behavior, and responsibilities so your scripts don't turn into a single giant file. That's exactly why the next lesson matters. Object-oriented programming is basically Python's way to help you build systems, not just quick experiments. Once you understand classes and objects, you can model real things, datasets, pipelines, models, experiments, as reusable components with clear interfaces.
And it's not just an academic topic. Even in data work, you often end up repeating the same patterns. Load data, validate it, transform it, compute metrics, save outputs. OP lets you package that logic so you don't copy-paste it everywhere. And so bugs don't multiply silently. Also, once you start working with libraries like scikit-learn, you're already interacting with objects all the time, estimators, transformers, pipelines. So lesson 10 is where things click. You go from writing code that runs to writing code that's organized, reusable, and easier to maintain.